So this is a recorded version of lecture 6. We forgot to live stream it. So we are recording it. All right. So in the last lecture, we have seen the notion of a cylinder object in a category. So let's recall. Let's recall if C is a category and X is an object, X is an object, then a cylinder structure on C is an object denoted cylinder on X with three maps E0 and E1 from X to X and P from still X to X such that P compose 0 is 1 on X and P compose E1 is also 1 on X. So the idea here was that we are trying to mimic the situation for topological spaces. So if X is a topological space, then the cylinder on X is X cross I. So if this is X, then this is X cross I, the topological cylinder. And then E0 and E1 are inclusion of X in the cylinder along the left hand and the right hand. This is E0. And then the projection map is this map P. Right. But if you note carefully, in all the examples that we mentioned, namely example 1 was the case of topological spaces where the cylinder structure on X was given by product with the control and the endpoints being given by the left hand and the right hand, E1, X cross I. So E1 was sending X to X comma 1 and E0 was sending X to comma 0 and P was simply the projection map to X. Whereas in the second case, the category chain complexes, the cylinder, if X is a chain complex, then the cylinder had the following components. Still on X dot. At degree n, it was given by xn, that x of xn, that x of xn minus 1. And the endpoint maps were given by sending it to the first copy and the second copy. And then so E0 was sending x to x comma 0 and this guy sending y to 0 comma 0. Whereas this guy was sending this map P was sending x comma 1 from z to x. The third example was that of category. The category, small categories, cat. There, the cylinder structure on a category was given by X product, which is contractible interval category. So J has two objects and an isomorphic. J in. So this is 0. Right. Well, if you see carefully, then you would notice that in most of the examples, the construction is actually functorial. By that, what I mean is that not only we are giving an object for every object x, and not only giving an object still x, but we are doing it functorial. That is, if there is a map from x to y, then we are actually also giving a map uh, from CLX to C. For example, in the case of topological spaces, uh, in case of topological spaces, the corresponding cylinder was x plus I, and uh, the map, if x is a map from x to y, then the corresponding map on cylinders was given by x plus I on I. So this is functorial, and this is the case for all of the other examples. Moreover, it is evident that the maps E0, E1, and P. So, with respect to x, if I denote this by x, then you can check easily that this guys constitute natural transformations. So E0 and E1 actually constitute natural transformations from identity to x, identity to cylinder, right? Constructed this way. And P is from cell to identity of C. And their naturality are really immediate. So instead of describing a cylinder structure on object basis, one can define cylinder structure for all objects together by saying that there is a functor cell which, when applied to object, gives you cylinder structure. So, therefore, we are going to modify the definition of cylinder object and make it a functorial description to be called a cylinder structure. So, a modified definition is as follows: if C is a category, if C is a category, then a cylinder structure on C is a functor cell from C to C with natural transformation E0 and E1 from identity on C to cell and a projection natural transformation from the functor cell to identity. So if you think of what happens in object-wise level, it says that for every object X, you have a map to cylinders. Not one, but two maps from X to cylinders. And here you have a map from X to X. So anyway, so that is the definition of a functorial cylinder structure. Well, in the recorded version, we had some discussion about when to call an interval contractible. Well, you see, in case of topological spaces, the interval is contractible, which in the description of cylinders says the following: that the projection map and the left-hand inclusion E0 constitute inverse homotopy. So first of all, it is immediate that P compose E0 is equal to identity. But moreover, E0 compose P is homotopic on X. So this is a very nice property of the topological cylinder. But the way we have defined a cylinder structure for an arbitrary category, it does not really look like that this homotopy equivalence holds. Remember, once given a cylinder structure on a category, we could define the notion of homotopy between maps. So the idea was the map in an arbitrary category C with a cylinder structure, F and G are homotopic if there is a map H from cylinder on X to Y such that H compose is equal to F and H compose P1 is equal to. And then you define something equivalent to homotopy equivalence as in case of logical spaces by saying that well, a map of topological spaces was a homotopy equivalence if it has a homotopy inverse. Similarly, in an arbitrary category, you say if F is a map from X to Y, this is a homotopy equivalence or still homotopy equivalence if there is a map in the reverse direction from Y to X such that F compose G is homotopy on Y and G compose homotopy on X. Now, in case of topological spaces, the cylinder was so nice that P and E0 constituted homotopy, right? And this homotopy was given by the following: H from X cross I, the cylinder on X cross I on the cylinder. So this is cylinder on cylinder. And the corresponding homotopy on X cross I was, well, so you must notice that this is the sequence. You start with X cross I, you apply P to land to X, and then you once again put by E. Therefore, to say that there is a homotopy from this to the identity on X cross I, you have to give you a map from the cylinder on X cross I to the cylinder such that H composed with the cylinder, H composed with the left hand inclusion of E0 on cylinder is equal to E0 from P, whereas on the right hand side, this is identity cylinder. And in case of topological spaces, this was given by the following data: H of X, S of T was given by X of S. So, therefore, to define a contractible cylinder in an arbitrary category with a cylinder structure, we should say that it's a cylinder structure such that there is a map from cylinder of X to cylinder of X such that this two condition, that is P0, sorry, E0 and P, E0 and P are homotopy. P are homotopy. Well, if you look at the topological case, then more is true, in fact, because you see this multiplication is after all multiplication of real numbers and that is associative. So in principle, we should expect that H is multiplicative. And moreover, the right hand inclusion E1 acts as a unit of this. by which I mean that h of x comma s, if you put equal to 1, then this guy becomes h of x comma s. So this part is E1. So uh, this is saying that H composed with uh, H composed with CIL of E0, sorry, CIL of E1 says that H composed with CIL H composed with E1 of CIL X is that concept. So the point is that this is not really enough to say that a cylinder structure on a category is compatible. One should rather require something called a monad structure to make sure that the corresponding homotopy is multiplicative or is of much more algebraic nature, and that this right-hand inclusion acts as a unit. So technically, one should say that technically speaking, a cylinder structure is said to be compatible if uh, there is a natural transformation. Well, you see in all of these cases, I was actually looking at a particular object X, and so like I can put X here and make it look like natural transformation. So if there is a natural transformation H, or I'll write M now instead, natural transformation M from cylinder of cylinder to cylinder, such that this condition is technical, you don't have to care about this. But let me finish this up. Such that cylinder with uh, M and E0, sorry, E1 is a monad on C, the monad on C. And moreover, this identity hold, that H compose E0 cell, H compose E0 cell is equal to E0B, which is equal to H compose cell of E0. So this is the technical part, but all that is happening is I'm trying to mimic a topological concept as well as the algebraic aspect of the cylinder. So a cylinder is contractible if it has a monad structure on the right-hand inclusion, which is uh, to say that the right-hand acts as the identity of this multiplication, whereas the left-hand acts as the zero of this multiplication. These are the two identities for zero. Okay. All right. So now one can, in principle, talk about multiple other things, but having cylinder structure really gives you uh, gives you a way to define several topological structures in arbitrary categories. So, for example, in case of topological spaces, there is a notion of mapping cylinder. A mapping cylinder is the following. Uh, so, if you are given a map f from x to y, then it is the following push-out diagram. You take the disjoint union of the cylinder on x and y and quotient out by the following equivalence function x comma 0 is equivalent to f. Pictorially, so if this is my y and this is x, then there is an image of x. I'll distort this. Better understanding. If this is my x, so if this is x and this is y, suppose this is f of x, then what you do is you glue f of x and x comma 0, the left end of the cylinder, and this is the right end. This is a mapping cylinder of the map f from x to y, which is equivalent to saying that the following is a push-up diagram. Similarly, in an arbitrary category, if you have a cylinder structure and a map f from x to y, then you can similarly define the mapping cylinder on f as the push out of this line. Well, once you define mapping cylinder, you may immediately think of suspension functor, right? So the ordinary suspension functor in case of topological spaces, the idea was the following: that you look at the cylinder on x, 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 and this is the cylinder on x. So what you do is you just smash out this two endpoints to different. You smash out this part, smash out to a single point, and you smash out the other point, this surface, to a single point, and what you get is like an enclosed sphere kind of thing by smashing out the two endpoints. But technically, what is happening is that you're looking at the two copies of x sitting inside the cylinder on x, this is the two copies, and then you're smashing out the first one to a single point and the second one to a single point, which is to say that you're looking at the disjoint union of the terminal map. So x2 star, there is a map psi x, star is the terminal map, terminal object, and there is this psi x, which is the unique map from x to the star. And by universal property, there is this unique map from x disjoint union x to star disjoint star. And what it means to smash out is to take the push out such that the left hand point collapses to star, the single point, and the right hand point also collapses to the single point. So this is the ordinate suspension on push out. So this is the mapping cylinder on psi x. Well, one can go on talking about this. But what is important is the following understanding that once you introduce the notion of a cylinder in an arbitrary category, you can talk of almost all topological constructions and topological results. For example, in the category of topological spaces, the understanding of homotopies and their consideration as being invariants for the purpose of homotopy theory is the construction of the homotopy theory, the homotopy category of topological spaces. So this is the category whose objects are topological spaces, all topological spaces, and morphisms found from x to y are the space of continuous maps from x to y, quotiented by homotopy. And this category is equivalent to the category of homotopy types. By that, what I mean, the objects are homotopy types, and homs are usual. On a chosen candidate. Okay? They're equivalent. The point is that they're and if you recall from lecture 1, there was this discussion about localization of categories, which mimic this concept for arbitrary categories. So if you are given category C with a class of morphism sigma, which in this case was homotopy equivalences, you can think of a category C of sigma inverse, denoted C of sigma inverse, where you have formally inverted all morphisms in sigma. So phi is such that phi of sigma are isomorphic. So in this case, in the case of topological spaces, homotopy equivalences were being taken to isomorphic. Right? And this was the smallest one among all such. And the smallest condition is stated as follows. If there is any other category T and any functor psi from C to P, such that psi of sigma are also isomorphisms in T, that is, say, psi of sigma is contained in iso, then there is a unique functor gamma, such that gamma composes phi. Right. So you can do all such things once you have defined cylinder structure, because then immediately you can talk about cylindrical homotopy as you have defined. Then you can similarly define the homotopy category of C as C localized at cell homotopy. Right? Well, if you see if the homotopy equivalence relation, if the homotopy relation given by a cylinder structure is an equivalence relation and it is well behaved with respect to composition, then there is no problem, right? Then there is no problem uh, in quotienting out. You can immediately quotient out by that relation and get the homotopy category. You don't have to think about this localization business. But in general, the homotopy equivalences need not be generating equivalence relation. The homotopy relation in general need not be an equivalence relation. Of course, this is reflexive. So F is homotopy to F. So if you have a map F from X to Y, then this is homotopic to itself by the following map. From cell X to X, this is D, and then you take F, and as H you take F compose. Then H compose E0 is equal to F, and H compose E1 is also F. So F is homotopic to F. However, a general cylinder structure has no reason to give you symmetric homotopy. But as we have discussed in the last lecture, this will be possible if you allow the interchange of the two endpoints, right? So if you allow so If you think of it as a topological space, then this is x cross I, and this is x cross I. So if you allow to have a map, which in this case was x comma t going to x comma 1 minus t, this reparameterization was the reason why the homotopy relation in case of topological spaces was symmetric, right? And what this guy was doing, it was sending the left end point x comma 0 to the right end point and the right end point to the left end point, right? If you allow that for an arbitrary cylinder, then this will immediately become symmetric. So what I want is a map from CIL X, or you can think of it as a natural transformation. I'll write X here, such that Ix composed E0x is E1x, and Ix composed E1x, then this would become symmetric. And how about transitivity? Well, the transitivity in case of topological spaces was coming from the following fact that you could break down a cylinder at the middle into two different cylinders. Namely, if you take this cylinder and break it down in the middle, then you get two different cylinders. So this is the one cylinder on X, and this is another cylinder on X. And you are joining, so this is the left hand point E0, this is E1. And for this cylinder, this is E0. So if you are taking the push out, that is, you are joining the left end of the second cylinder and the right end of the first cylinder together, then what you should get should be homotopic equivalent to the cylinder on X itself. If you allow that, then this would become transitive. So I invite you to write it down formally what it means to have a subdivision exercise, subdivision of a cylinder. All right. So this is our discussion about cylinder structures and cylinders. But importantly enough, there is a striking and a different viewpoint of uh, of homotopy theory of topological spaces. So normally, when you talk about homotopy between the continuous map, we describe it as follows. So if X is a topological space, we are thinking of the cylinder sitting on top of X. This is X, and this is the cylinder. And suppose we want to have a homotopy between two maps F and G from X to Y. Then what we are doing is basically this: given a point X, we are looking at the line sitting on top of X. So this is X cross I. Okay. This X cross I. And the homotopy is mapping this line to a path, something like this. So this is Fx. So this is the bottom end, E0x. This is the right end, X. This is Tx. So a homotopy is a map from the cylinder to Y, right? But you see, this data of having a cylinder is actually superfluous. You don't even need this data that there is a line on X on top of X, which is being mapped to a path. You can straight away see that well, a homotopy is rather mapping every point to a path on Y. And by a path on Y, we mean a continuous map from I to Y. So homotopy is a map from X to the space of continuous maps from I to Y, which maps a point X to the path starting at Fx and G. So there is a map H from X to the space of continuous maps such that when you evaluate, so if you look at H of X and you evaluate it at 0, the left hand point you get Fx, and if you look at the right hand point of Hx, then you get G. Right? So this is a different viewpoint of talking about homotopies of topological spaces. Well, one thing one should keep track of that this map has to be somehow continuous, and for that we need to put some topology on the space of continuous maps, and the best candidate for that is compact topology on the function space. Okay, so yeah, so there is a different way of discussing homotopy theory for topological spaces. Instead of using cylinders, one can use the idea of path objects, path spaces, and one can, in principle, abstract out this property of path spaces to abstract categories. So let us do that. Okay, so just a minute. Instead of calling this EV1 and EV0, let me call this as left hand L0, and let me call this as L1, just to shorten the notation. So if you have a category, abstract category C, then a path object on X, which is an object in C, is an object denoted path on X. Okay, I'll write it for Y actually. Path on Y is an object with two maps. Well, of course, there is this projection map. So this is L0 and L1. So path Y, from path Y to Y, there are two maps, L0 and L1. But there is this obvious constant loop map. What it does is it sends a point Y to the constant loop on Y. And moreover, L0 compose C is identical, and so is L1 compose. And similar to cylinder structure, we define a path structure as being an object path on Y with two maps with maps L0, L1 from path on Y to Y, and C, the constant loop map from Y to path. Okay. So, and such that L0 compose C is equal to L1 compose is equal to 1. And what this is doing is that it is factorizing the diagonal map. In case of cylinder structure, the cylinder structure was factorizing the co-diagonal map. In this case, this is factorizing the diagonal map. X, sorry, Y to Y plus Y. Y to Y plus Y. It is factorizing the diagonal. Right? This is L0 plus L1, and this is okay. And in this case, you say that two maps are homotopic, X to Y, two map F and G are homotopic if there exists a map from x to path y. So here in this case, it was map from x to path y. So it's a map from x to path y such that L0 composite is equal to L1. Sorry, this is F, and L1 composite of G. All right. And equivalently, one can define the notion of homotopy. Great. But the question is, in case of topological spaces, you did have the fact that there is an equivalent notion of doing homotopy theory in terms of path spaces. But how about the other example? For example, category chain complex. Does there exist a path structure? And the answer is yes. So the path structure, I'll just describe it. If you have a chain complex y dot, then the path structure at degree n is given by yn plus 1 direct sum yn direct sum. And differentials one has to figure out whether there exists one, or in other words, the path space on y dot is given by the chain space from I dot. So the objects, the terms in this chain complex are degree n maps at degree n. And how about the category of categories? Well, the path structure on y dot, sorry, on a category y, is the category functors and natural transformations from J to Y. And you can check that they show that to map or maps in this case are homotopy equivalents, if and only if they are homotopy equivalents along this path structure, and a functor in cat, a functor from C to D is a homotopy equivalence along this path structure. Is a homotopy equivalence. It's a homotopy equivalence along this path structure. If and only if the cylindrical equivalent and this is if and only if the categorical well, so is the case for chain complexes, and so is the case of topological. So, to sum up all these things together, I'm going to define something called a pre-homotopy theory. Definition. A pre-homotopy theory is a category with both a cylinder structure and a path structure such that they're compatible. Meaning what? The path space functor is right adjoint to the cylinder. Well, in case of topological spaces, you had a cylinder blank cross I is actually left adjoint to, here I'll write it, still left adjoint, is left adjoint to the function space. Uh, blank I or path in case of top. This was the case. In case of categories, the same was the case. Blank with this interval j is left adjoint to the path space from the j comma blank, and in the category j. Tensor product with the standard interval I is left adjoint to the path space counter, which is the chain space I dot blank. So this means that all of these three are pre-homotopy. Great. So far, so good. But this is not really true that all theories are pre-homotopy. There are, of course, theories which just has cylinder structure or has a path structure only. There is no cylinder structure associated with it. So if it has a cylinder structure only, then we say that it's a left pre-homotopy theory. Or it has a, if it has a path structure only, then we say that it's a right pre-homotopy theory. Well, sometimes we would emphasize that the cylinder structure is contractible and the path structure is contractible. Make sure that nice topological results would arise. Okay. All of these theories are, after all, both left and right pre-homotopy. But if you recall the case of an additive category and a monad being given T epsilon mu, there the cylinder was actually given by the following functor blank direct sum T blank. This is not a pre-homotopy. Well, because there is no reason for this cylinder to have a right adjoint. So even if there is a path structure, if you can find out, there need not be a right adjoint to T. So unless T preserves all four, this is not a pre. So I'll end this session with the proposed example of a left homotopy theory, which is not right homotopy theory, but has a new insight. So consider the category C, the category of groups. My claim is that there is a left homotopy theory left pre-homotopy on the category of groups, meaning that there is a path structure. So the path structure is the following. If G is a group, the path structure on a group G, G only, is the following. Is the pair x comma y, collection of all such pairs, such that x and y belong to G and x, y inverse belong to the commutator. Show that these are the groups. Obviously, this is this one. But why is this a path structure? Because, well, uh, if you look at G, then there are two maps from G to path G, which is send G, there is a constant map which sends G to G comma G. Well, G and G inverse, G compose G inverse is of course identity that will belong to the computer subgroup. So this lands indeed inside path G. But from path G to G, there are two projections, PR1 and PR2. So the first one maps G comma H to G, and the second one maps G comma H to H. Clearly, PR1 compose C is equal to 1, and PR2 compose 1. So immediately, you conclude that this gives you a path structure in the category groups. My claim is the following. Claim. Collect all homotopy equivalences that you can from the path structure. So the sigma, or look at path homotopy equivalences along this path structure, following the definition just as here. Okay. You define homotopy equivalences and collect them together, and you look at the corresponding homotopy of groups along this path. That is the category of homotopy types in the category groups along this path structure. And my claim is that this is precisely the category of evidence. Well, the reason is the following. If you take a group G and you look at its abelian addition, which is G modulo the commutative subgroup, then this is the homotopy. P is a homotopy. I'll leave it as an exercise to check that P is a homotopy. This is a nice exercise. But the point is, once P becomes the homotopy equivalence, once you invert all homotopy equivalences, the homotopy type of a group becomes the corresponding abelian transition, and therefore the category of homotopy types in the category of groups along this path structure, as mentioned here, becomes precisely the category. Prove that. Prove the claim. It's a nice exercise. But now what it does is it changes the viewpoint of ordinary mathematics that we have been working on so far. It says that most of our subtheoretic understanding are actually a result of some sort of homotopy theory, which no one ever pointed out previously. Maybe this is not the only one. You can take the category of pre-sheaves. There is also another example. Take the category of pre-sheaves on a topological space. Then you can define a path structure on a pre-sheaf. So the path object on F on an open set is again given by pairs of sections S comma T, such that germ of S at X is equal to germ of T at X for all X. There are of course this obvious projection maps to FU and a constant map S comma S from FU path FU, and it gives you a path structure. So much so that the corresponding homotopy category, the homotopy category of pre-sheaves on X along this path structure is precisely the category of sheaves on X. And many more, the homotopy category of monoid is the category. there is a path structure. So most of our sub-theoretic understanding can be given in terms of homotopy. So that is the point that I wanted to make. However, this is not a pre-homotopy theory. This is just a blessed pre-homotopy theory. That need not be a right pre-homotopy theory. But nonetheless, it is a part of homotopy. Okay. I'll stop.